Hello everyone, welcome back. In the previous lecture, we have seen the Laplace transform, a basic concept of Laplace transform, and some elementary problems which can be directly solved with the help of definition of Laplace transform. Now, in the lecture number 2, we will discuss about the Laplace transform of some standard functions. So, by definition of Laplace transform, we have seen if f of t happens to be a real valued function, the Laplace transform of f of t is given by integration between 0 to infinity e to the power of minus st f of t dt. Now, by using this particular definition, we can find the Laplace transformation of some standard functions. So for that, let me take one example. Let f of t as e to the power of at, which is an exponential function. So here t is a variable and a is a coefficient, non-zero coefficient. So by definition, Laplace of f of t, as we know, it is 0 to infinity e to the power of minus st f of t dt. Now wherever f of t is there, that I am going to replace it by e to the power of at. So accordingly, integration between 0 to infinity e to the power of minus st dot e raised to at dt. And from algebra, we know that it can be expressed as e to the power of minus s minus a times t dt. Now we are integrating exponential function with respect to t, and the coefficient is s minus a along with a negative sign. And accordingly, so here e to the power of minus s minus a of t divided by minus s minus a between 0 to infinity. So we can take out this particular denominator factor outside. So that is minus 1 divided by s minus a, and what is remaining? E to the power of minus s minus a times t between 0 to infinity. As we have integrated with respect to t, so we will be replacing the variable t once with a infinity and then with a 0. The moment when I replace t with infinity, the entire factor becomes e to the power of minus infinity, and when we replace t by 0, it becomes e to the power of minus 0. Now minus 1 divided by s minus a, so this will remain unchanged. The value of e to the power of minus infinity as 0, whereas the value of e to the power of minus 0 as 1. So on solving, so we will get 1 divided by s minus e. So here we observe that the Laplace transformation of e to the power of at as 1 divided by s minus e. So here we can rewrite like this: the Laplace transform of e raised to at is 1 divided by s minus e, and of course s is greater than e. So this is just one of the result, or we can call the Laplace transform of e raised to at as 1 divided by s minus e. So from this result, we can talk about some sub results. So those are known as corollaries. Suppose if I replace a to be a 0, that means s is greater than 0. So here e raised to at 1 divided by s minus a, in that if I am going to replace a to be a 0, so what will happen? E raised to 0, and what is e raised to 0? That is 1, and that a equal to 0 I am going to replace even on right hand side. So accordingly, we will get the Laplace transformation of 1 as 1 divided by s. And further, in e to the power of at, if I am going to change the sign of the coefficient a as a minus a, then we will have Laplace of e to the power of minus at, that is equal to 1 divided by s minus of minus a, which in turns 1 divided by s plus e. So we have seen the Laplace transform of e raised to at is 1 divided by s minus a, whereas the Laplace transform of e raised to minus at is 1 divided by s plus e. And we know that e to the power of at or e to the power of minus at, both are the exponential function. So similarly, we can obtain the Laplace transformation of some standard functions. Like, apart from exponential function, we come across frequently the trigonometric functions such as sin at, cos at, even the hyperbolic functions sin h of at, cos hyperbolic at, and as well as algebraic functions t raised to n. All those functions, we consider them as a standard function, and we will apply the same formula the same Laplace transformation technical definition, and we can talk about the Laplace transformation of each function. Now, when we talk about the Laplace transformation of those standard functions, and when we find all the standard functions and together we can represent them in the form of a table, that is the Laplace transformation of standard functions. So here we can observe two columns. The first column definitely apart from serial number function, and the other one is Laplace transformation of that particular function which has to be considered here, that is f of t, and L of f of t, it gives f of s. So first we will start with a 1. So 1, sometimes instead of 1 we can even have a constant k. Okay, so that is Laplace of 1 as a 1 by s. By using that particular rule or particular technical definition, and when we operate, we come across Laplace of 1 as a 1 by s. Similarly, Laplace of e raised to at. So just now we have seen Laplace of e raised to at is 1 divided by s minus a. E to the power of minus at is 1 divided by s plus a. So both the results we have seen. Now, let me talk about the sine at. The Laplace of sine at is, the coefficient of t is a, so it starts with a divided by s square plus a square, whereas Laplace of cos at, s divided by s square plus a square. So we have done with the trigonometric functions. Then apart from trigonometric functions, we have sine hyperbolic of at, that is a divided by s square minus a square. Similarly, cos h of at as s divided by s square minus a square. So here I would like to point out just one important point. Sine of at. When we talk about the Laplace of sine of at is a divided by s square plus a square, whereas sine h of at, that is hyperbolic function, it's a divided by s square minus a square. Everything is same except the sign convention. So whenever we have the hyperbolic function, the denominator between s square and a square, we will come across with a negative sign. The same pattern we can observe even in cos at. Laplace transform of cos at is s divided by s square plus a square, whereas the Laplace transform of cos h of at is s divided by s square minus a square. So what's the difference? So only difference is in the denominator between s square and a square, we have a negative sign. So, and wherever it is cos h of at or even cos of at, the numerator always comes with s. Okay, in both the cases the numerator will come with s, and whereas sin h of at and sin of at, where the coefficient of t was a, so the numerator will comes with e. Okay, so that's the pattern one can remember. Now, apart from trigonometric and hyperbolic functions, we can have an algebraic function, that is t raised to n. So Laplace of t raised to n. Now what is n? So we have the two different situations. N either positive integer or we may have a negative integer. So let's talk about the generalized form. Laplace transform of t raised to n is gamma of n plus 1 divided by s to the power of n plus 1. And there is a one more situation when t raised to n can be taken, and the Laplace transformation of t raised to n is n factorial divided by s to the power of n plus 1. And when we talk about the n factorial, we always seek n to be a positive integer. So whenever n come across as a positive integer, we adopt this particular formula, that is Laplace transformation of t raised to n is n factorial divided by s to the power of n plus 1. And apart from positive integer, whenever we come across a fraction, we always prefer the Laplace transform of t raised to n to be gamma of n plus 1 divided by s to the power of n plus 1. And also we have gamma of n plus 1 as an n factorial. That's a general observation that we have seen in gamma and beta function also. Okay. Now with this Laplace transformation of some standard functions, as I was talking, Laplace transformation of standard functions, and we have identified one, that is a constant, then e to the power of at or e raised to minus at as an exponential function, sin at or cos at as an trigonometric function, sin h of at or even cos h of at as an hyperbolic function, and then we have considered algebraic function. So all these functions are considered to be a standard function, and we have identified the standard functions along with their Laplace transformation, which forms the building block for the entire Laplace transformation contains. With the help of these Laplace transformation of standard functions, in the next lecture, we'll discuss about some fundamental property known as linearity property, and we'll talk about the problems which are based on linearity property. So for more information and problems, please comment and don't forget to subscribe, like and share. Thank you.